Here we have a block diagram, same as we've seen on the previous slides. This is the standard form. K, GP the plant, feedback unity with a negative. Input R of S, output Y of S. We want to draw the root locus. This is the plant. It's given in the problem. GP is equal to 1 over S plus 1 times S plus 3. Clearly, the open loop poles are at negative 1. It makes this term go to 0. And negative 3 makes this term go to 0. The first thing we want to do to draw the root locus is put the denominator of the closed loop transfer function in the 1 plus k times something form. Standard block diagram simplification rules are what? K GP over 1 plus k GP. K GP over 1 plus k times GP. This is the denominator of the closed loop transfer function. Y of S over R of S. 1 plus k times 1 over S plus 1 times S plus 3. I brought it down here. This is the form we always draw the root locus for. 1 plus k times something. All the rules are developed for this form. 1 plus k times something. Our first step is to do a pole zero plot for what's inside the bracket. Do we have any poles? Yes, we do. Negative 1, negative 3. Negative 1, negative 3. I use x's for poles. Do we have any finite zeros? No, we do not. We don't see any circles on the plot. Our next step is to shade the portion of the real axis which belongs on the root locus. We start over here as far as we can move, and we move to the left because our rule says shade to the left of an odd number of poles and zeros. We start moving, we hit the first X. That's 1, I count 1 X. Shade. 2, do not shade. Keep moving, stop. The only portion of the root locus which lies on the real axis is between negative 3 and negative 1. Now we continue with this example. Step 3, as we've seen before. Calculate the centroid and then find what the asymptotes look like. The centroid formula is the sum of the poles minus the sum of the zeros over the relative degree. We go back one slide. What are the poles of the something? Notice I always go to the 1 plus k times something form. The poles are negative 1, negative 3. Negative 1, negative 3. Minus the zeros. There are no zeros. That's why in this problem you don't see any more numbers. So I have negative 0, which can be left out. Where does this 2 come from? That's the relative degree. The relative degree of the something is 2, because if we multiply out the denominator, the highest order is s squared. S to the 0 is in the numerator. S squared minus s to the 0 as far as the degree is 2. So the relative degree is 2. That's why we have this 2. So I put the 2 in the denominator. I got minus 3 minus 1 over 2 is negative 2. So the centroid will be at negative 2, this number right between negative 1 and negative 3. Now how do we know that the asymptotes move straight up and down like this? We go back to our asymptote chart. For relative degree equal to 2, the asymptotes are straight up and down, like this. Go back to our example, and we can see the asymptotes are anchored at negative 2, and they move straight up and down. We have now prepped the plot. We are now ready to draw the root locus. And we remember these 3 rules as we draw it. The locus must be symmetric about the real axis. We have 2 zeros at infinity because the relative degree is equal to 2. And the locus must start at the open loop poles, which are the x's, and move to the zeros, which can be circles or at infinity. And remember, we have, for this problem, 2 zeros at infinity because the relative degree is equal to 2. So I'm now ready to draw the root locus. And remember, this portion of the root locus must be on the real axis, so it must be part of the, it is shaded, so it must be part of the root locus. So I draw it according to these rules, and it must have this shape. One portion of the root locus starts here at the x and moves and goes here, and the other portion must go here and move straight up. Now you might say, does it really have this corner? Yes, it does. It must have this corner here. The blue and the green must have a corner here because we must not violate this rule. The locus must be symmetric about the real axis. So we draw the blue and we draw the green and they hit, and then one closed loop pole goes along this asymptote to infinity. We're following this rule here, and one closed loop pole moves here and moves straight up to infinity, following this asymptote, again following this rule. So what happens? As k is equal to 0, one closed loop pole starts here, one closed loop pole starts here, and as k is increased, the two closed loop poles meet together right at the asymptotes, and then as k is increased further, one moves up here and one moves down here as they become complex conjugates. And then finally, as k is further increased, they move further and further until they get to infinity when k reaches infinity. So what does this picture tell us? It tells us that for all values of k, the system is stable, because the blue and the green represent closed loop pole locations which will always have negative real parts. There are no pieces of the root locus in the so-called right half plane to the right of the j omega axis. Anything over here, closed loop poles would have what? They would have positive real parts. This green represents a possible closed loop path which will always have negative real parts. The same is for the blue. The blue represents a path which, if any closed loop pole lies on that path, it will have negative real parts. So what we can say is the closed loop system is always stable. The closed loop poles always have negative real parts.